Have you ever looked up at the night sky and wondered where it all came from? How did this vast universe teeming with billions of galaxies, stars and planets come to be? The answer, my friends, lies in a profound and awe-inspiring event that happened roughly 13.8 billion years ago, the Big Bang. Now, the Big Bang wasn't some giant explosion in the sky as the name might suggest. It was something far grander, far more fundamental. Imagine, if you will, all of space and time compressed into a single, infinitely dense point, a singularity. This singularity contained the seed of everything we see around us today. Then, in a fraction of a second, this singularity began to expand, an expansion of space itself, and with it, the birth of our universe. In the first fleeting moments after the Big Bang, the universe was an unimaginably hot and dense soup of energy. As the universe expanded and cooled, this energy began to condense into particles, the very building blocks of matter. First came quarks, then protons and neutrons, the constituents of atoms. This marked a critical step in the evolution of the universe, setting the stage for the formation of stars, galaxies, and ultimately, life itself. In the first few minutes after the Big Bang, the universe was still too hot for atoms to form. Protons and neutrons collided at incredible speeds, constantly being created and destroyed in the inferno. However, as the universe continued to expand and cool, a critical threshold was reached. At around 380,000 years after the Big Bang, the universe had cooled enough for protons and neutrons to combine and form the first atoms, primarily hydrogen and helium. This event, known as recombination, had a profound effect on the universe. The sea of free electrons that had previously scattered light like fog cleared, and the universe became transparent for the first time. The light, freed from its interaction with the primordial plasma, has been traveling through the cosmos ever since. Today, billions of years later, we can still detect this faint afterglow of the Big Bang, known as the Cosmic Microwave Background Radiation, or CMB. Think of the CMB as an echo of creation, a baby picture of the universe when it was just 380,000 years old. By studying the subtle variations in the temperature and polarization of this ancient light, cosmologists can piece together the conditions present in the early universe and test our models of cosmology. The CMB tells us that the universe was remarkably uniform in its infancy, with only tiny fluctuations in density and temperature. These tiny fluctuations, amplified by gravity over billions of years, would eventually give rise to the large-scale structure of the universe we observe today: galaxies, clusters of galaxies, and vast cosmic voids. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery that revolutionized our understanding of the universe. By observing distant galaxies, he found that they were not fixed in space, but were moving away from us. Moreover, the farther away a galaxy was, the faster it seemed to be receding. This observation led to the development of Hubble's law, which states that the universe is expanding. The expansion of the universe is not like the explosion of a bomb, where fragments fly outward into pre-existing space. Instead, it's the fabric of space itself that is stretching, carrying galaxies along for the ride. But the story doesn't end there. In the late 1990s, astronomers made another startling discovery. The expansion of the universe is not slowing down as one might expect due to gravity, but rather, it is accelerating. This acceleration is thought to be driven by a mysterious force called dark energy, which makes up roughly 68% of the total energy density of the universe.